Hello everyone, I'm Li Sun. Today I will present our work, WiDraw, enabling hands-free drawing in the air on commodity Wi-Fi devices. This is a collaboration work with Shavik Shen, Q-Han Kim from HP Labs, and Dimitrios Kotsonikolas from University at Buffalo. So the popularity of smart devices calls for an easier way for human-computer interaction. Comparing with remote controllers or mice, it is easier for humans to control devices with gestures. Today, we can use gestures to control laptop, TVs, and we can also play video games with gestures. It is expected that we will use human gesture to control more home appliances in the future. So today, we can use camera devices like Kinect or Leap Motion to track human gestures. And we can also ask users to wear devices like smartwatches, rings, or RFID tags. Recently, researchers have demonstrated that we can track human gesture by capturing the fluctuation of wireless signals. Although this approach doesn't support none of such scenarios and doesn't require the user to wear any device, it still needs software-defined radios or projector training. So we believe if we can enable hands tracking on an existing mobile device without using cameras, wearables, or customer radios, we can make using hand tracking more popular. So in our work, we propose to use a commercial network card to track human gestures. We propose WiDraw, which enables hands-free drawing. WiDraw can track arbitrary gestures. It supports 3D tracking. More importantly, it only needs a software patch on a mobile device with wireless network card. The main idea behind WiDraw is to use a large number of Wi-Fi devices in today's wireless lines. Each Wi-Fi device can work as a signal source. The evolution of Wi-Fi technology allows us to use a network card to extract CSI when receiving a packet. We can further use the CSI to calculate angle of arrival. So now let's assume a user is sitting in front of a computer, and the user's hand blocks the path of angle of arrival. Then we will observe a sharp signal drop on the path of angle of arrival. And this gives us an intuition to localize the hand at a given moment. The user device can get multiple angle of arrivals from neighboring devices. When the user's hand is moving following a trajectory, it may block a few angle arrivals. So on the time domain, we will observe the received signal strength minima on the LAs blocked by the human's hand. And the order of the RSS minima experienced by LA blocked by the human hands will indicate the hand trajectory. So in the previous example, I made a few assumptions. We assume we have known the 3D AOE values, and we have known the hand depth, and the hand will block the LA completely in the movement. However, in practice, to make this system work, we still need to solve those problems one by one. So the first task is to estimate the 3D AOA. AOA value is a 3D value consisting of azimuth and elevation. However, most of a mobile device use a linear antenna array, which can only report a 2D AOA, which is the projection of the 3D AOA on the antenna plane. And there exists a geometrical relationship between the 2D AOA theta and the elevation and azimuth values. To estimate the 3D AOA, we ask the user to rotate the device along the z-axis in the antenna plane as shown in this figure. In this procedure, the elevation angle will keep constant. And the 2D AOA and the azimuth value will gradually change. In this procedure, we will log the maximum AOA, the maximum 2D AOA, and we observe that when the 2D AOA achieves the maximum, the azimuth is 90 degrees. At that moment, according to the geometric relationship we built before, we can calculate the elevation angle directly. So after that, a 3D AOA can be calculated with a known elevation and a measured 2D AOA. After rotating the laptop once, we can calculate all of the 3D AOAs we need later. The second task is to estimate the human depth. To convert azimuth and elevation to a 3D Cartesian coordinate, we need to know the hand depth, which is the hand distance to the antenna plane. So our solution is to calculate the RSSR drop for each AOA when the hand is presented in front of the screen, and then calculate the average RSSR drop. In our experiment, we put the hand with a large number of x and z coordinates, and then tested it at different depths. We found that there exists a linear relationship between the average RSSR drop and the depths, which can be used to estimate the depth value. We can further refine the depths by analyzing the timing differences when the hand across the neighboring AOAs. So for the details, please read our paper. So the final task is to refine the coordinate. So this is because when an AOA experiences an RSS minima, it may be because the hand pass by this AOA instead of blocking it completely. In that case, it is not accurate to use the AOA's coordinate to represent the hand's location. So our solution is, we first studied the relationship between the hand distance to the AOA in the 3D space, and study its relationship with the RSSR drop. We observed that there exists an exponential relationship between those two factors. And this factor can give us an intuition about where is the hand. For example, when AOA 0 experiences an RSSR minimum, at this moment, we can estimate the hand distance to this AOA. So this hand can be on a circle with a radius equal to the distance we calculated before. However, we still don't know where is the hand. To further localize the hand, we take a look at the other AOA's RSSR trend. So for example, in this figure, suppose the AOA 1's RSSR is increasing. This means our hand is moving away from it. And at the same moment, we know AOA 0 experiences RSSR minimum. So that means the hand is not moving towards it or moving away from it. So we can get two moving directions which are tangent to this circle. For another example, at the same moment, AOA 2, the RSSR is decreasing. This means our hand is moving towards it. Then we get another two tangent directions. The RSSR increasing or decreasing speed indicate how important a moving direction is. We repeat this procedure for the remaining neighboring AOAs, and then assign a weight for each direction considering the RSSR decreasing or increasing speed, and then aggregate all of the direction together to get an aggregated direction. Combining the distance calculated with the RSSR drop before with this aggregated direction, we can get a new refined location. So now I'm going to talk about WiDraw's performance. WiDraw can track lines, curves, letters, words, and even 3D gestures. In our implementation, we use a laptop with Atheros AR9590 network card. We use leap motion to capture the ground truth. We analog WiDraw's each track pointer's arrow, and we also evaluate WiDraw as a handwriting application. So we first study the impact of AOA density. This is because WiDraw's performance depends on AOA density. Since all of the AOAs point to the central point, to the reference point of the linear antenna array, it is true that the AOA density will decrease with fewer transmitter or larger depths. In the study of the number of transmitters, we tested 2D lines, curves, and circles. We found that WiDraw's median error can be as low as 4.7 centimeter if using 25 transmitters, and its tracking error can be lower than 5 centimeter if using more than 15 transmitters. For the depths, we found WiDraw's performance, WiDraw's tracking error can be lower than 5 centimeter if the depth value is smaller than 60 centimeter. Second, we study WiDraw's performance in 3D tracking. We draw a large number of 3D and 2D lines and curves. We found that WiDraw's accuracy in distinguishing the 2D and 3D gestures is quite high, and its median tracking error is 8.6 centimeter in the 3D case. Finally, we use WiDraw for text input. We tried letters, words, and sentences. We use MobiCom stylers as the recognition application, and we use Monkey Runner to connect WiDraw with MobiCom. We first tested the input range and depth. In this application, we ask users to draw 2D text in a plane in front of the antenna plane. The depth value is the user's hand to the antenna plane, and the horizontal value is the x coordinate as shown in this figure. So by studying different depths and horizontal range, we found that the letter recognition ratio is higher than 0.9 for the depth value smaller than 60 centimeters, and the horizontal value smaller than 50 centimeters. We further studied the letter width. We found that if the letter's width is higher than 30 centimeters, the letter recognition ratio for both uppercase and lowercase letters can be higher than 0.95. Combining with the horizontal value we got before, this means a user can write up to 3 letters continuously on each line. So for the words with more than 3 letters, we will connect a word segment through a bottom line. Then we will sample the word by removing the bottom line. We asked 3 users to input 1,000 words. We found that WiDraw's accuracy is higher than 0.9 for the word with fewer than 4 letters. Finally, we asked 10 different users to input a paragraph with 100 words. We found that on average, the word recognition ratio is higher than 0.85. So in general, we propose WiDraw, which is the first hand tracking solution on a commercial Wi-Fi network card without prior training. And WiDraw can enable hands-free drawing in the ear using AOAs. WiDraw even supports 3D tracking and high accuracy text input. So thanks for your attention.